Very good morning, friends. In the previous class, we have discussed viscous flow between two parallel plates where both the plates are at rest. And also we have solved one problem on that. In this class, we will go to the next derivation, that is flow of viscous fluid between two parallel plates. Again, you may think that the title is same, but you just observe here, one plate is fixed and another plate is moving. So this type of condition where one plate is moving and another one is at rest, in between these two plates, whatever the flow occurs, that is called as Couette flow. Couette flow means it is the flow in the passage between two parallel plates where one plate is fixed and another plate is moving with a uniform velocity u. The same figure is shown here. You can see the upper plate is moving plate with a uniform velocity capital U, whereas the bottom plate is stationary plate which is not having any velocity. Consider a small element ABCD as shown in the figure. Let the force acting on the face AB of the fluid element is P into delta Y into 1, and the force acting on the face CD is P plus dP by dx into delta x into delta y into 1. And BC and AD are the faces parallel to the plates. On them, the shear forces are acting and the corresponding expression is shown in the figure. Compared to the previous figure, here the velocity distribution is not as like of previous one where at the center the velocity was higher, but here in this type of Couette flow, the velocity will be higher nearer to the moving plate, whereas at the plate surface, there will be the velocity which is equal to the plate velocity, and at the stationary plate surface, the velocity of the fluid is equal to 0. So this is what velocity distribution observed and shown in the figure. Now, the forces acting on the fluid element we have discussed. For steady and uniform flow, there is no acceleration and hence resultant force in the direction of flow is 0. So resultant force in the direction of flow means it is nothing but force in the direction of positive x direction, where equating all the forces in that x direction, that is P delta y into 1 minus opposite force to this positive x direction is P plus dP by dx into delta y into 1, where 1 is taken as a unit thickness. Shear stress minus tau into delta x into 1, that is on the upper surface, on the bottom surface, that is you can see on the face BC, whereas on the face upper face AD, the shear force is tau plus d tau by dy delta y into dx into 1. Equating it to 0 and simplifying, we will get the following equation. And again dividing this equation by delta x and delta y, we will get the final equation of pressure distribution, that is dP by dx is equal to d tau by dy. Velocity distribution is derived from the pressure distribution because we know that Newton's law of viscosity tau is equal to mu into du by dy, where dP by dx is equal to d by dy of mu into du by dy. Therefore, mu into d square u by dy square is nothing but dP by dx. Because this is d tau by dy, tau is replaced by mu into du by dy. Integrating this above equation twice to get the value of u U is the expression for velocity distribution. Again, you are having some constants of integration C1 and C2 in this expression. These constants are removed by applying the boundary conditions. At y is equal to 0 at bottom plate, velocity u is equal to 0, and at y is equal to b, velocity u will be equal to the plate velocity capital U. Substituting and solving, you will get the both constant C1 and C2 values. Again, substitute both C1 and C2 in this velocity distribution equation. Then you will get the final expression for the velocity distribution as U is equal to capital U by B into y minus 1 by 2 mu dp by dx into by minus y square. Rearranging the above equation, we get u by u is equal to y by b minus 1 by 2 mu dx dp by dx into b square into y by b into 1 minus y by b. Whereas this term is taken as it is shown on the under brace, that is p is equal to minus b square by 2 mu u dp by dx. It is nothing but a non-dimensional pressure gradient. Means it is a pressure gradient where it doesn't have any unit. Replacing that term as p, we can write the velocity profile in a non-dimensional form. Non-dimensional form means this equation of velocity profile doesn't have any of the units. That is u by u is equal to y by b plus p into y by b into 1 minus y by b. Now, you see that for simple shear flow, there is no pressure gradient, okay, in the direction of the flow. So pressure gradient will not be there. When p is equal to 0, capital P, so that is non-dimensional pressure gradient, capital P is non-dimensional pressure gradient. So thus, using this condition, the above equation reduces to velocity distribution to that of velocity of flow u by u, which is equal to y by b. This is known as simple Couette flow. So this indicates that velocity distribution is linear as shown in the below figure. You see that there is a linear or a straight line. Velocity varies in a linear scale, whereas it is 0 at the stationary plate and maximum at the top plate, where top plate is moving plate. It can be produced by sliding a parallel plate at a constant speed relative to the stationary wall. So top plate is a parallel plate moving with a constant velocity u. Therefore, you will get the linear velocity distribution as shown in the figure. This is for the Couette flow. The velocity profiles for various values of p are shown in the figure 3.1. So u by capital U is plotted on the x-axis, capital U on the again top plate x-axis. So there are two plates. This is a bottom plate. So for the bottom plate, you have to consider u by u. For the top plate, only u. Here u is equal to 0 because it doesn't have any value, because this top plate is moving with a capital u velocity, uniform velocity. Now, these are the velocity profiles for various values of p. P is a non-dimensional pressure gradient. So that is shown in here. For p less than 0, u by u is negative. For p greater than 0, u by u is positive. And this happens because the fluid motion created by the top plate is not strong enough to overcome the pressure gradient in the first case. Whereas in the second case, the fluid motion created by the top plate is strong enough to overcome the pressure gradient. So this is the expression for the velocity gradient. We have continuation of this expression as a maximum and minimum velocity and its location. You just see that u we have derived. So this is the expression u is equal to capital U by b y plus P into capital U by B into Y minus Y square by B, or delta U by delta Y is equal to U by B plus pressure gradient, that is non-dimensional pressure gradient, into U by B into 1 minus 2Y by B. So for maximum velocity, delta U by delta Y is equal to 0. There is no velocity gradient for maximum velocity, and Y by B tends to half plus 1 by 2P from the above expression. Again, it is interesting to note the maximum velocity for P is equal to 1 occurs at Y by B is equal to 1, and it is equal to U for P greater than 1. Maximum velocity occurs at location Y by B less than 1. This means that for P greater than 1, the fluid particles attain a velocity higher than that of a moving plate at a location somewhere below the moving plate. And for P minus 1, the minimum velocity occurs at Y by B is equal to 0. For P less than minus 1, the minimum velocity occurs at location Y by B greater than 1. Means occurrence of the backflow nearer to the fixed place is shown in the figure 3.12. Maximum and minimum velocities are shown in the above figure. The maximum velocity will be U max, which is capital U into 1 plus P square by 4P, and minimum velocity will be U minimum, capital U into 1 plus P square by 4P. These are for conditions P greater than or equal to 1 or P less than or equal to 1. Now we have to derive the volume flow rate. For fluids, we generally calculate volume flow rate. So Q is equal to 0 to H integration between limits U into dy, where U expression is substituted here from the above velocity distribution equation. After integration with the limits, finally we will get Q as 1 by 2 plus P by 6 into UH, where average velocity is Q by A. It is continuity equation Q is equal to area into velocity. Rearranging U is equal to Q by A, that is velocity is equal to volume flow rate divided by area. So Q expression as 1 by 2 plus P by 6 UH divided by area is 1 into H, unit thickness into height of the gap between two parallel plates. So average velocity is 1 by 2 plus P by 6 into U. Therefore, for P is equal to minus 3 from this above equation, the discharge will become equal to 0, and the average velocity U bar will also be equal to 0. So this is what the expression for the Q. Next expression is the shear stress distribution. We know that tau is equal to mu into du by dy. It is a Newton's law of viscosity. You substitute this du by dy from the above equation 3.28. You will get the following expression. Simplifying, after substituting the value of P, finally we'll get the shear stress distribution tau as mu into U by B minus 1 by 2 dP by dx B minus 2y. Here, this type of flow is discussed is known as generalized Couette flow, where the flow of viscous fluid between two plates, one stationary and another moving, is possible. Last three expressions are force, torque, and power. The force is derived using the shear force or viscous resistance, which is equal to shear force into area of the surface of the shaft. Shear force is mu into du by dy into area. Du is pi dn. Pi dn is the velocity. Dy is 60 into t. Pi dn by 60 is u. T is the thickness, that is dy. Area is nothing but pi d into L. We have to consider. Therefore, substituting, we will get force is equal to mu into pi square d square n L by 60 into t. Torque is nothing but force into radius, that is viscous resistance multiplied by d by 2. and that is nothing but above expression of force multiplied by d by 2. Therefore, d square will become d cube in the torque equation, and 160 will become 120 because denominator is multiplied with a 2 and numerator is multiplied with a d. Power absorbed in overcoming the viscous resistance is torque into omega, angular velocity. Torque expression as it is, you substitute in the following power expression. Omega is nothing but angular velocity 2 pi n by 60. Substituting the finally we will get P is equal to mu into pi cube d cube n square L by 3600 T. So kindly go through this above expression. In the next class we will derive laminar flow through circular pipe, that is called as Hagen-Poiseuille equation. So this one is Couette flow. Next one will become in a circular pipe laminar flow, that is called as Hagen-Poiseuille equation. Once we complete this Hagen-Poiseuille equation, we will come on to the problems of the Couette flow as well as the Hagen-Poiseuille equation. So go through this video several times until you get familiarized with the derivation. Thank you.